along and give us a presentation of your view on quantum mechanics. I mean, I talked to him yesterday, and he has really a rich career, both as a physicist and epistemologist and manager and computer science and complex systems. So I allow myself to help myself with the reminder here. So he graduates from École Polytechnique and also did telecommunication studies, graduated, and then he defended a thesis in theoretical physics. This was about unification between the strong and electroweak interaction. That's something which is still very in focus. He did it in University of Paris in '88. Now, there is a different types of career, some of which are scientific, the other is professional. Maybe I just mentioned that he was a deputy director of General NEF. Is this something with the health insurance, or it's a defense, or?
Yes, that's linked with health. Yeah, with health.
Okay. Yeah. And then he was chief executive officer of Styria Group. He also founded companies which studied complex system, which is still running. He founded this in 2000. But more interesting for us, of course, is scientific career. So there are some, I will just read. He was associate researcher of the Institute of the History of Philosophy since 2001. He has been also attached to the Applied Mathematics Laboratory of École Normale Supérieure in Paris-Saclay from 2002. Founding member of the Philosophy of Science Society, founded in 2002. He also co-developed a research program on emergence of cognitive capacities complex systems from 2002 on. Also, he was a president of the Collège de Physique de Philosophie, which is a founded initiative by Bernard de España, who was also your mentor and a colleague.
Yeah.
And I think he influenced very much your views on quantum physics and nature. Yeah, and he was associate professor at the physics department, University Paris. Help me, yeah?
It's Paris 7. University Paris 7. Yeah.
Paris 7, okay, good. So, I mean, I know you mostly from the work on your interpretation of quantum mechanics. You had a very visionary views on the notion of reality and perception in quantum mechanics that I think partially have been now confirmed by the series of no-go theorems related to Wigner's friend, extending Wigner's friend situation, and I guess you were going to talk today about that. Thank you very much. I think you don't need, you have your own?
No, because this is for the outside, but for inside, I think that I need. No, you hear me? Okay, very good. Okay. Okay, very good. So I would like first to thank Czeslaw for his kind invitation. I'm very glad to be here with you to talk about the subject. As I told him yesterday, I'm very glad to have people to speak with about the subject because there are not so many people interested in that kind of stuff. And sometime in Paris, but Paris is a big city, but on this subject, there are not so many people interested. And then when I speak with my colleagues, very often they say, okay, well, I don't agree with all this stuff around Wigner's friend and all that. So it's not so easy to speak about the subject. And I'm very glad to be here, mainly because Czeslaw was one of the first to reactivate the interest in this kind of thing. So thank you very much, Czeslaw, to have invited me. So I'm going to give a talk about many different topics around this subject, mainly the non-absoluteness of events, perspectival interpretations, second order facts, and all that kind of things. The reason is that there have been many recent works about Wigner's friend, especially extended Wigner friends experiments, and no-go theorems based on those experiments. The first one was from Czeslaw, and then many have followed. And they seem all to lead to a kind of non-absoluteness of events. That's something that I want to discuss. Emily Adam sorted the problems in three kinds of disaccord, what she calls type 1, type 2, and type 3 disaccord. I will explain what that means. Timothy Riddle also says that in this case we have to choose between time or feral interpretations. And I will present at the end my interpretation. This is an interpretation initially coming from an idea from Bernard Espagna a long time ago, but I have started developing in 2000, which is called Convivial Solipsism. This is not solipsism. That's Convivial Solipsism, which is totally different, and which is supposed to solve the measurement problem, but which finds a lot of support in all these new works. So this is the reasoning I'm going to follow. First, extended Wigner no-go theorems seems to give a sort of kind of proof that events are not absolute. Of course, modulo some other hypotheses. The first question that we can ask is, what does that mean? What it is to be non-absolute? Because that's not so easy to understand. That's not obvious at first sight. So we have to think about the meaning of this non-absoluteness. Then I will plunge a little bit in more details on what Emily Adam calls type 3 disaccords, which is also something that we can state as the violations of what Matt Leffer called the tracking assumption. I will explain what that means. And if we violate these tracking assumptions, then we go into what Timothy Riddle calls feral interpretations. And I will then finish by presenting very briefly my interpretation, Convivial Solipsism, which is maximally perspectival and feral. As Charles told me yesterday, I'm a little bit extreme in that interpretation. I think that it's necessary. Okay, so I'm going to be to go quickly on this stuff because everybody here, I think, knows that very well. So I start with the Wigner-Friend experiment with a physicist in a laboratory performing a quantum measurement. Then Wigner's is external, and the contradiction comes from the fact that Wigner, following the universality of quantum mechanics, attributes a superposed entangled state vector to the friend, the system, and the labs. And more precisely, if I say that the measurement made by the friend is of a qubit prepared in a superposed state of the computing basis, then when the friend is measuring the system, the qubit, it will find either 0 or 1 with a probability half. And Wigner, at the outside of the lab, should assign the entangled state phi plus, which is a superposition, of course. And the disaccord, and that's what Adam calls a type 2 disaccord, comes from the fact that if we interpret the entangled state vector intuitively, then that doesn't correspond to what the friend inside the lab has perceived. There is a disagreement between the natural and intuitive interpretation of this phi plus state and the fact that the friend inside the lab has perceived something precise. And that's what she called a type 2 disaccord, mainly because this intuitive interpretation gives a false image of what the friend has perceived, but we can say that this phi plus is nevertheless giving right predictions for every measurement that you can do on the friend alone. It will be exactly the same, and if you have a large number of trials of measurement of the friend, you can measure what you want, you will be in agreement with what you find with this phi plus. So the disagreement comes from, first, the fact that you interpret that in a way that is not correct from the friend's point of view. And the second thing is that if, and that's what you do, if you make an experiment not on the friend alone, but on the friend plus the system, then you have a disagreement between two possibilities. The first one would be to accept that there is a projection, and in this case, Wigner should have a proper mixture description of the friend plus the system, and not an entangled. And there is a distinction between the prediction that you can do, of course, if Wigner adopts a proper mixture, and if he adopts the entangled state. But for making this difference, you have to make a measurement on the global system, not on the friend alone. Okay? And Adlam says that this is easy to solve. That's not a real problem. And she says that it is strange only because we are confusing two different sides of the state vector. What she calls the intrinsic state, which is supposed to refers to the actual physical state of the system, and what she calls the interaction state, which encodes predictions about the result of measurement. And she says that usually there's two sides of the state vector are confused. They are always think together. And that if we want to understand what happens here, we have to separate the two and to say that the entangled state is not the intrinsic state, it's the interaction state for Wigner. And she says in this case, there is no more problem. I'm not totally convinced that it is solving everything, but that's interesting to separate the two roles that the state vector can have, the role of describing the physical state of the system, if you are realist, of course, which is not the case for many people working in this field. And the second one is just a prediction tool. And in the usual and historical way to understand the state vector, there's two roles were confused. No, I don't agree with that. But that's the description she gives, mainly, I think, because she tries to stay, to keep realist. Yeah. So the type 2 disaccord comes from the following reasoning. We refuse the projection postulate. Okay. And why? Mainly because the measurement problem and the impossibility to give a clear specification of what the measurement is. Okay, there is a problem here. Okay, so reject the projection postulate, but assume that the projection postulate is correct. For example, assume that you have a GRW interpretation, which could be the case. We don't know yet, even if it doesn't seem that it will be confirmed, but we are not sure yet. Or assume, it's always possible because nobody has proved that it is impossible, that we find a solution of the measurement problem inside the usual quantum mechanics. Then Wigner, knowing that his friend got a result, should adopt a proper mixture description. Okay? And as I said before, a measurement of the observable with eigenvector phi plus is the entangled description I gave before, phi plus phi minus on the global system will not give the same result for the proper mixture and for the entangled state. In the first case, you have probability half to get each result, while in the latter one, you have only one, the first one, which is certain. Okay. So universality, which is the fact to adopt the phi plus description, in fact, is empirically testable, even if it's totally out of reach, because the measurement apparatus would be a little bit difficult to build. But in principle, it could be possible to test that. Now I'm going to place myself inside the mainstream, which is to accept universality and to reject projection postulates. So I will not consider spontaneous collapse theories, hidden variable theories, and multiple outcome per observation interpretation, such as Everett. I will just not consider them. And I will start inside, the reasoning will be the following. I will start inside a non-modified formalism of quantum mechanics. at the beginning with or without projection postulate, and a single result per observer during a measurement. Then we can see, as I said, that this position with psi-realism leads to a contradiction because of the measurement problem. So at the end, if we start from this very broad and open position, we are finally led to what Matt Leffer calls the Copenhagen-Algish interpretations. What are the Copenhagenish interpretations? They are described roughly by 4 properties. The first one is observers observe. What that means, there is one definite outcome that an observer gets during a measurement. I think that everybody is happy with that, and there is no problem. The second one is anti-psi ontology. The quantum state does not represent the intrinsic property of the system. A large category of people agreed with that, not Emilie Adam, because she proposed to deal with the intrinsic state. But I think that many people will agree with the fact that today it's difficult to maintain the fact that psi is really describing the system such as it is. Some people are still saying that, but not the vast majority. In Paris, they are saying that. My colleagues in Paris. Completeness. There is no deeper description of the world that to be had besides QM. That means we don't consider hidden variables in general sense. And universality. Universality, everything can be described by quantum mechanics. There are no non-quantum systems. And the dynamics is unitary, and the Bord rule allows to compute the probability of measurement outcomes. That is something that is much less accepted easily by people. I had 2 weeks ago a conversation about that because I invited at the French Academy somebody you perhaps know, which is with Philippe Grangier. And Philippe Grangier, when I speak with him, says that universality is totally crazy. That cannot be true. And he's not alone. Franck Laloué, perhaps you know him also, has written a famous book of quantum mechanics, which is the book for all the students. He says, okay, universality is a mistake. It cannot be true that you can describe an observer by quantum mechanics. So I don't want to speak about that. And they stop the discussion. So this is something that is more difficult, and this is an obstacle that you have to go through before starting to discuss all what I'm going to say. And there's people very often don't want to speak about that because they say universality in broad sense is not possible.
If I may just interrupt.
Yeah.
There is a very nice refined version of that by Asher Perez, who said anything can be described.
Yeah.
Not everything.
Yeah.
Because there must be external measurement apparatus, somebody who will take the data for it.
Yeah. And this description is perfect. Because when we say that anything can be described, that means that you can describe also an observer, but you have to keep something outside. And this is what we are going to speak about. Okay. So I use, I think, a more precise and good description from Adlam of what she calls first-person universality, and this is the definition I will use in the following. Unitary quantum mechanics is universal in the sense that it is always a correct description of all observations made by any individual observer, but it does not describe the relation between observations made by different observers. Here we should allow that the observations made by an individual observer, Alice, may include reports made to Alice by other observers about the outcomes of their own measurement, or records that she consults about observations made by other observers, which may be modeled quantum mechanically as interactions between Alice and other observers' record, or as measurement by Alice on other observers' or record. And I totally agree with that. And I put that in bold, I have put that myself in bold. Alice has no direct access to observations made by others. And that will be important for the following. So our only information about them comes from the result of our interaction with other observers or records. And thus, first-person universality requires only that Alice's own measurement outcomes are correlated with the results of Alice's measurements on observers' record in the way that quantum mechanics dictates. First-person universality does not require that Alice's outcomes are correlated with the actual observations made by the other observers in any particular way. Therefore, first-person universality places no constraints on the relations between observations made by two different observers. And she adds, and I put that in red because I don't agree with that, she adds, except in scenarios where there is some subsequent interaction or measurement in which the observers are able to share information about their outcomes. And that's contradictory. Either you say that there is no relation between different observations, or you say that you can share information. And she started by saying that there is no relation, and then she finished by saying, unless observers are able to share information. And that's part I disagree with her. And I know why she wrote that. This is mainly because she absolutely wants to keep the possibility to share information, and namely that's the additional assumption that she made inside relational quantum mechanics with Carlo Rovelli, with CPL, which is cross-perspective link, which allows people to share information in reality, and which allows them to have intersubjectivity again, which that is something she wants because she is a realist, and I don't agree at all with that. And I don't agree with this additional assumption of CPL in rational quantum mechanics. I think that it's ad hoc assumptions that is not really well founded. I think that what she wants to say is, okay, we start separately and there is no relation between us. But if after we meet, then we can have at that time. I think that it is what she means. I'm not sure, but I think that it is what she means. And I don't agree because, as I will explain in more details, even if we meet after, we'll have the illusion to agree, but that will not be real. Okay. So I switched now. I'm not saying that, but the first picture was from the Kirchhoff paper, and this is a picture from Bong and colleagues' paper. Extended version of Wigner's fan, and of course you all know that, so I go quickly on that. So you have two versions of Friend and Wigner jointly, and they share a pair of entangled particles, and a few assumptions which are crucial for the proof. Of course, the universality of quantum mechanics, and what they call local friendliness. That's absoluteness of observed events, locality for observed events, no superdeterminism, and also the fact that a super observer can undo a measurement. That's something that is for people, experimentalists in Paris. That is something that is totally crazy. Yeah. So the experiment is the following one. Charlie and Debbie in two different separate labs are sharing each one a particle coming from a pair in the Hardy state, the entangled Hardy state. Okay. Charlie and Debbie each measure their particle in the computational basis, and they can get the result, which we call C and D. Now Alice and Bob are external, and Alice can choose between asking Charlie which result he got, opening the lab, and after asking Charlie which result he got, which is what we call the choice X equals 0, or he can undo Charlie's measurement and measure the particle in the orthogonal basis, plus, minus. And that's the same for Bob. Okay. And in this case, that's the choice, y equals 0 or y equal 1. And at this stage, what we can say, following directly from the usual and basis of quantum mechanics, that we have, there's probabilities. It's very easy to see that. Probability that C equal 1 and D equal 1 if x equals 0 and y equals 0. That means in the case where Alice and Bob chose to open the lab and ask their friend which result they got, equals 0, and the same in the other situation. Okay, so we have these 4 equations that are very easy to prove. Now, before going to the demonstration, I just come back to the assumptions that are made. Absoluteness of observed events. In the paper of Bong et colleagues, they say that it is an observed event is real single event and not relative to anything or anyone. Okay, that's large. That could be understood in many different ways, but that the usual and intuitive way we use when we say an event is absolute, that's what we mean. Okay. And more precisely, they say that that means that it exists a joint probability for the 4 events A, B, C, D, depending on X and Y, of course. And first, the probability of A and B is the sum of the probability of A and B and C and D, sum on C and D, okay? And also, and that's what Matt Leifer called the tracking assumption, probability of A, C, if C and D and X equal 1 equal delta AC. That means mainly if Charlie, if Alice opened the labs and asked Charlie what he got, what Alice is going to hear is exactly what Charlie got. That's written mathematically, but that is the meaning of this equation. That means nothing else. So that is something very natural. If I ask my friend what he got, I'm going to hear something that corresponds to what he got. Okay, and that's the tracking assumption on which we are going to come back, because that's the key of the following. Just a side remark. The conjunction of absoluteness of observed event and universality leads, I think, to attention, because it's not clear or it is possible that when an observer carries out a measurement, obtain a single and absolute result if the observation is a unitary process. That is something that we can understand in perspectival interpretations. Because in this case, the unitary description is for the outside, not for the observer himself. And in this case, it's possible to have both universality for the external and a measurement inside or for the observer. But if you are in the usual scheme of the standard quantum mechanics, where everything is absolute and everything is real and things like that, it seems that it's not possible to have both absoluteness of observed event and universality. Okay? And this is something that is often neglected. That's not analyzed really in many papers. Now, the other assumptions, locality for observed event and no superdeterminism, that's what they call local agency. No superdeterminism is the fact that probability and C and D doesn't depend on X and Y. Roughly, that the measurement that Charlie and Debbie make is not correlated to something that is outside in the future cone. Okay, and locality is the usual way to define locality. That is the probability of A doesn't depend on the probability of what the probability of what Alice will observe doesn't depend on what Bob will observe, because it's outside of its light cone. Okay, and the same for Bob. That's classical, usual. Okay, so now we can see that we get very easily a contradiction. I go quickly on that. We start from the first four equations. Then the locality for observed event helps you to transform those equations with equations where there is only x and y equal to 1. That means that in all these cases, you are going to have Alice and Bob having undone the measurement of the friends and made a measurement in the orthogonal basis. Okay, and in this case, the absoluteness of observed events said that these measurements are all observed, really observed events. So we have 4 events that have been really observed. Okay, and then I don't make explicitly the reasoning that you can follow here. Then you can see that you get a contradiction. Okay, so as soon as you get a contradiction, you have to abandon one of the assumptions. And let me just before make a few reservations. The first one, as I said, is that in the universal version of quantum mechanics, it's unclear what a measurement is. Okay, I said that before. The second one is there is a kind of metaphysical problem when, and this is what we say here, when we say that Wigner undoes the measurement done by Charlie, and nevertheless, the measurement done by Charlie is still a fact. Okay, that's what is supposed here. That's not so easy, because if you, well, undoing the measurement of an observer is something like that is similar to going back in the past. And in this case, you change the past in a way. So that's not so easy to accept that without any reservation. But okay, that's what many people do, and we'll do that also. And of course, real experiences are totally out of reach, and that is obvious. So if you want to abandon one of the assumptions, usually what we do is abandoning the absoluteness of observed events. And in this case, that will lead to some epistemological problems. I will come back to it after that. And in convivial solipsism, observers don't agree on outcomes. In reality, I will explain what that means. And if they speak together, yeah. Oh, sorry, don't disagree. Sorry, you're right. Excuse me. Don't disagree. Don't disagree on when they talk together, they agree. But as I will explain, as strange as it could be, they don't disagree, but that doesn't mean that in reality they have seen the same thing. And I will explain how it is possible that to be the case. So let's start from the definition given by Bong and colleagues. An observed event is a real single event and not relative to anything or anyone. What does it mean that we deny that? That means that there is no fact of the matter about which outcomes of a measurement actually occurred, because a measurement can have different outcomes relative to different observers. And then Adlam and also Bong and colleagues says that this global assumption can be decomposed into 2 different assumptions that she calls AOE1 and AOE2. AOE1 is just that there is a well-defined value for the outcome observed by each observer. That is, I don't want Everett, for example. Okay. And AOE2 is what I called before the tracking assumption. It is the fact that when Alice asked directly Charlie which result he got, what she hears is really what Charlie got. And this is the small equation that I've written before. Okay? So if you want to deny A or E, you have to deny at least one of the two. Denying A or E1 would imply multiple outcome per observation, which we don't want. So that means rejecting A or E2. That means rejecting or violating the tracking assumptions. And that leads to what she calls type 3 disaccords. And there is a point that is not clear at this point. Bong and Adlam seem to agree on the fact that this tracking assumption is included in the absoluteness of observed events. And Matt Leifer says not. And I don't understand exactly what he says. Because he says that the tracking assumption is independent of the absoluteness of observed event, and that it is not needed to derive the no-go theorem. And in the version of his paper where he presents the no-go theorem, it doesn't use this assumption. And in the version that I have presented, which is the version I took in Leifer's paper, I don't use the tracking assumption. That's true. But for proving that it is independent, he gives the example of parallel lives, where the tracking assumption is satisfied, even though the absoluteness of observed event is not. But I think that he is wrong, but I have to discuss with him about that. I'm prudent. Because that's not a proof of independence, that's the proof that A or E is a sufficient condition, but not a necessary condition. And in fact, in the example he gives, what is violated is A or E1 and not A or E2. So I'm not sure that his argument is good. Okay, but that's a side point. So in the following, I will accept that rejecting the absoluteness of observed event means rejecting the tracking assumption. So if you want to say that events are not absolute, you are led to think that when two observers discuss, what the first one hears from the second one is not necessarily really what the second one has seen. Okay? And this is what Adlam calls, this time, type 3 disaccord. So let's go briefly into this 3 types. I don't know why she numbered that this way, because type 2 disaccord, this is the first I mentioned, the fact that the entangled 5+ description of Wigner's inside the lab is something that is not intuitively corresponding to the fact that the friend has perceived something precise, but nevertheless can be in agreement with any measurement you do on the friend. Okay, and she calls that type 2 disaccord. Okay, but the type 1 disaccord and the type 3 are roughly the same. So I don't know why she said 1, 2 totally different, and 3 the same. I would have numbered that differently, but that's not important. So what she calls type 1 disaccord is principally the fact that Charlie performs a measurement. Alice also conducts one measurement on something that is correlated to the measurement that Charlie has made. And Alice then used the result of her measurement to infer something about Charlie's measurement. Okay? So she measures something, and she used quantum mechanics to say, okay, according to quantum mechanics, I saw that it was correlated to what Charlie did. So, okay, I think that Charlie saw that. That's what she calls type 1 disaccord, when the result she infer doesn't correspond to what Charlie really saw. Okay, and the type 3 is exactly the same thing, excepted that this is not a measurement on something that is correlated. It is a measurement directly on Charlie. She is asking Charlie. And she says that type 3 is a special case of type 1. Okay. Okay. So that's the case that interests us. We will be interested in. Okay. how many time I have? How much time I have? Okay. Oh, okay. 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 Yeah. Okay. 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 So I'm going to accelerate. I'm going to to accelerate. Okay. So I'm going to skip that. That's just the way she tries to save the absoluteness of observation. A first point that is important, and that's a point that I discussed a lot with Eric Cavalcanti, and we were not in agreement on that. How is it possible to notice the disagreement? If you say that Alice made a measurement and Charlie made a measurement and that they cannot have access to, who is able to say that's different? Neither Alice nor Charlie, okay? So when we state the tracking assumption, we have who is able to state that. And this is possible only from a meta-observer point of view. Okay, you can call it as you want, but it is necessary to allow to speak from this meta-level point of view. And as Timothy Riddle says, facts about what is the case relative to this or that observer are absolute. If it was not the case, the tracking assumption could not even be formulated. Roughly, that means that, of course, the result that Charlie got is relative to Charlie. But if Charlie got plus, for example, the fact that Charlie got plus is an absolute fact. That's what I call second-order fact, and those second-order facts are absolute. Otherwise, you cannot state the assumption. And this is something that was a hard discussion with Eric Cavalcanti, who think first that the tracking assumption should not be violated, and so that you have not to mention this meta level. And he even goes, if I understand him properly, he even goes further. He told me the fact that I refuse that you speak from this meta level doesn't allow you to say that the results are different, so they are the same. And this is what he wants. Actually, what he wants is keeping this tracking assumption to have this intersubjectivity preserved. And well, and this is a tough point because I don't understand why, even if there is no real observer at this meta level, of course, no observer is able to be at this level. But from the point of view of the people who is building the interpretation, you are outside, so you have the right to speak at the meta level. And that's exactly the same the situation then when, as a mathematician, you are building an axiomatic formal logic system. Okay, inside this formal logic system, you have certain expressions, certain formula that you can state and you can prove. But it is necessary when you build a formal axiomatic system to mention the properties of the formal logic system, and those properties are formulated at the meta level of the system. This is something that is very well known in logic. And I think that we are in the same situation here. Even if physicists are less used to use these notions of meta level and things like that, I think that it is necessary in this case. So we have to be able to speak at the meta level to mention the fact that the results are not the same, even if no observer can witness that. Okay. Just a point very quickly about the intersubjectivity and empirical confirmation. It seems, according to Adlam, that if you don't have this intersubjectivity, because you can get results and I can get different results on the same experiment. So she says, okay, in this case, science is not possible. And why? Because the confirmation of the scientific theory comes from the fact that we share the same facts. And if we don't have the same result, it will not be possible to have that. I think that it's not true, essentially because what we need for the confirmation of theories is not to have exactly the same result, is to have the same relative frequencies. If you do a series of experiments on the system and you have your results, I have mine, they can be different. But if, if the relative frequencies that you have coming from results that are different from mine, but are in accord, confirming the Born rule, then both of us will confirm the Born rule and the quantum mechanics. And I think that it is enough. So that you don't need to have exactly the same individual result for confirming. Yes? Yeah. 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 That's true. The point is that if you confirm, and I have confirmed on my side, then if we talk together, I will hear you saying that you have confirmed also. Yeah, but that's a subtle point. There could be a problem, and that's something that can be discussed because. Yeah. Yeah. You're right. You're right. What I say means that frequencies are real. Yeah. I don't know. That's a good point. Well, that's something we have to think about. That's not clear. And what she says is that if you want to confirm a scientific theory like perspectival interpretations, in which each observer has his own perspectival point of view, then to confirm that, you have to have an element saying that all the perspectival will be structurally equivalent. That's a little bit like saying that relative frequencies are the same, are real. And she said there is no reason, we cannot know that, and perhaps I will see relative frequencies in according to Born rule, and from your side, it will be totally different, and we cannot know that. So that undermine the possibility to confirm scientific theory. Yeah. 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 Well, that's not easy to have a clear answer to that. Yeah, I agree. Yeah, yeah. And well, and she wants to have intersubjectivity, and she at the end what she wants to do is to keep the absoluteness of observed events, because what she proposes according to the no-go theorems is to keep absoluteness of observed event and to abandon superdeterminism, no superdeterminism, because she wants to introduce a kind of retrocausality which opens the door to many other problems. Okay, so if we abandon the tracking assumptions now, we are open to what Riedel classified the different interpretations. He says that a perspectival interpretation is tame if facts about the outcome of a measurement is relative to some particular observer are absolute. That is what I said. Second order facts are absolute. And there is no iteration of relativization. That is something that he proposed in one paper. For example, in rational quantum mechanics, he says, okay, everything is relative to one system, but the fact that it is relative could be relative to another system and ad infinitum. Okay. And that's strange because if you want to think about what that means, that's very difficult to understand or to give a meaning to that. So you have no iteration of relativization, okay? An observer can communicate a perspective. That's you respect the tracking assumption. If you respect those two situations, then you are in a tame interpretation. That's a gentle one. Now, what he calls a feral interpretation is first you can iterate ad infinitum relativization, which I will not consider here, or you violate the tracking assumption. And what he says is that if you are in a tame interpretation, then you are subject to what he calls a revenge theorem. He says that it's not enough. Even if you are perspectival but in a tame manner, then you are again subject to a no-go theorem. So you have no choice than becoming feral. That means you have no choice. Either you accept the relativity to higher orders, which I don't want to do, or you have to give up the cross-perspective communicability, the tracking assumption, AOE2, that sort of thing. Okay. So that's a little bit stronger than what is said usually. And I'm not sure, but from the discussion I had with Eric, I think that he doesn't like that because he don't want to be feral. So that's open. I'm not sure I have to discuss with him again, but in the paper he wrote, I think that he tries to keep this this possibility of communicating. And apparently, but I have to be sure, I'm interested if any one of you has read this paper, if you are convinced or not by this revenge theorem, which states that even if you are in a perspectival interpretation which assumes that the results are relative, it's not enough to escape the no-go theorem. That's stronger. I don't know if you are aware of that or not. No, nobody has read that. Okay, that's a point important because if it's true, and I have to be sure, it seems convincing, but I have to read more carefully and to discuss with people. Perhaps something I miss. But if it's true, that means that we have no choice than to abandon the tracking assumption, and I'm happy with that because that's exactly what I do in the interpretation. That I developed well before all these no-go theorems. I started developing that, unfortunately, in a French book I wrote in 2000, and as it was written in French, the audience was narrow. And then I wrote a series of papers, all that on this interpretation. And at the time I started developing that, the extended Wigner friends were not at all a fashion. What I was saying was very often considered as crazy, because I was already mentioning the fact that people are seeing things that are relative to them, and then when they speak together, they agree, but that doesn't mean that they have really seen the same thing. And everybody is saying, well, okay, HERVE is crazy, okay. And I'm very, very happy now, because all these new theorems are supporting this idea that I had many years ago. And to be honest, the first idea of convivial solipsism came from Bernard Espagna in a book he wrote in 1967, where he criticized Everett interpretation. And he tried to find a way to avoid the multiplication of words. And that's coming from this remark that I developed that. And well, I discussed a lot with him, but unfortunately he died in 2015. Okay, so the first thing is that initially it was intended to solve the measurement problem, which I think that does. I'm going to explain how. This is in agreement with all what we have seen before. The reality is relational. Quantum states are defined in relation to a particular observer, never absolutely. And there is no view from nowhere. This meta level is necessary to speak of the interpretation, but there is no observer able to see everything, and namely to witness the result got by other observers. Okay, I'm going to skip that. So let me just give you the way it solves the measurement problem. You have, that's the usual description of the measurement problem. You have a system which is described by phi, an apparatus initially in a ready state A0, and the environment E0. And when they interact, they are entangled, and you get this entangled sigma Ci, Phi, Ai, Ei. Okay. Now, the question is, how is it possible from this entangled state to get one result? And the solution I propose is the fact that due to the limits of perception, an observer can only be aware of one component of the superposition. And this component is chosen at random according to the Born rule. That means that the state is not changing. But when you look at a system or at a global system to which you have attributed an entangled state, then the only possibility due to our limits, that's a perceptual limit, is to see one of the components in the preferred basis, which is defined, if you want, by the decoherence of things like that. Okay, and the probability is given by the Born rule. Okay, this gives. This is what I call the hanging on mechanism, and I say that a measurement is nothing physical. It's the fact that an observer selects in his perception one component of the superposition. And in this case, that gives a clear criterion to define where and when a measurement arises. What is the problem in the measurement problem? It is not possible to know exactly what is a measurement. And is it a physical process or not? I say it's not a physical process, it's just a perceptive process. Yeah. Yeah. Okay, you can use this picture. That's different from Bohmian mechanics, of course. But at this point, you could describe that in a similar way. I agree. Yeah, you're right. Yeah. But that's not important. All the stuff around Bohmian mechanics is not present in my interpretation. And what I want is just providing a criterion that explains why, at a moment, an observer has a result. And you can find that natural or not, because many of my colleagues in Paris don't want at all price to have the observer playing any role. They want to have a description of quantum mechanics as in classical physics. The world is there, and the observer is only somebody who arrives and who observes, but he witnesses things that are there. Okay, and when you say no, things are not there, the observer is playing a major role in making things appearing for him. Okay, they close the door and they go away. So the first thing is I say, okay, we describe some system in an integral way, and the measurement is only the fact that if I measure that, I have a perception of one component. And in this case, you can, of course, find that strange, you can accept it or not, but this is coherent. This gives a criterion that is clear and which solves, in a way that some are not appreciating, but in a way, the measurement problem. Okay, and I'm just going to give you an image. Okay, have a look at this picture. Okay, and tell me who is seeing the dancer spinning clockwise. Yeah, that's spinning, and you can see the dancer spinning clockwise or counterclockwise. And okay, and counterclockwise. Okay, so usually that's the case that around half of the room sees the dancer spinning clockwise, and the other half counterclockwise. And that's just an illustration, of course, that's a very limited picture. But in this case, what happens? This is something that is interpreted by the brain differently according to people. Some people select one direction of rotation, and other people select another one. And I use this example to show that, assume a sort of image, that it is a superposed situation where the dancer is spinning in a superposed way, clockwise and counterclockwise. Some of you are seeing them clockwise and the other counterclockwise, but nobody is able to see her spinning in both directions. That's not possible. Our brain is not equipped for that. Okay, so I don't pretend that this is a proof or that this is something that is more than a simple picture, but that gives an image of what that means when you are confronted to something that is ambiguous for the brain, that the brain selects at random something. And I say that it's the same when you are in front of a superposed system. Okay, that's just an image to make you understanding what I mean. Okay, so the hanging on mechanism is that process of selection. And once the awareness of an observer is hung on to one branch, it can hang on only to daughters of this branch for all the subsequent observations. And of course, this guarantees that repeating the same observation will give the same result, which is necessary in quantum mechanics. This is totally respecting universality. An observer has to be treated by another observer as a potential measurement apparatus. That is nothing else. That is a physical system. And an observer has no direct access to another observer's perception. Okay, that's what we saw before. And that was the founding on the interpretation well before Allday's no-go theorem. So there are two principles, the hanging on mechanism and the relativity of state. Everything is relative, and that's similar to cubism, to rational interpretation, and things like that. Okay. Now, we start from the wave function. An observation selects one of the possibility, and the possibility that is selected is relative to this observer. And the collapse becomes only a selection by the observer of one possibility among several. Okay, and the extended Wigner's friend scenario provides compelling argument for this view. Now, and that's the important point, there is no disagreement between observers. See, if Alice interrogates Bob, then she will get a consistent response from what she saw before, and that's easy to prove because she will be in the global wave function where Alice, Bob, the system, and so on are entangled. Everyone is inside, is on branch, and so when they communicate, they always agree. That's the reason why I have called that convivial. Nobody's fighting. Everybody's in agreement with everybody else. So that's a smooth word. Very good. Now, that doesn't mean that Bob have obtained the same results. And this is a fundamental principle, and I had many criticisms coming from colleagues or even from referees for publishing papers in reviews at the beginning. That was not so easy because of the confusion And many referees answered, oh, your position is contradictory because, and they stated sentence where they have in the same sentence, they use the result from one observer and the observer, the second observer. And of course, you don't have the right to do that. If you speak from the point of view of one observer, you can only mention either your direct observations or what you hear that the other says of their observation. But you cannot, you have not the right to say, I am Alice, I saw that, and Bob saw that. It's not possible. You can say, I am Alice, I saw that, and I heard Bob saying me that he saw that. And that's the main point of difficulty. And I remember Chris Fuchs saying that he had the same problem at the beginning with cubism, where many people were not understanding that that is personal. And okay, I think that now things are more clearer. But of course, we need the meta level to speak of the tracking assumption, and I allowed myself to mention the result of two people, but at the meta level, not inside the interpretation. Now, that's a very strange description of reality, because reality is not at all the same than the usual one. We have what I call the empirical reality. The empirical reality, everything is relative to one observer, but the empirical reality is all the potentialities that the observer could describe, could actualize by a measurement. And that's described by a global entangled wave function. And that's in the universal, in the Everett interpretation, that's what they call the universal wave function. But the main difference is in the Everett interpretation, the universal wave function is real, and the same for everybody. And here, the relative entangled global wave function plays the same role, but it's not real. It's just a kind of potentialities, a set of potentialities, and it's relative to one observer, and two observers have not the same one. Okay, and the reality in the usual sense is what I call the phenomenal reality. Phenomenal reality is what each observer creates by his measurements from his empirical reality. So you have your empirical reality, which is the set of potentialities that you can actualize. Then you make measurements, you get results, and those results are what constitutes your phenomenal reality, and that is what you usually call your reality. You live in that. And this reality is yours. It's not the same than your neighbors. But if you speak, then you will agree. That doesn't mean that from the meta-level point of view, you see the same thing. But you'll always agree. So we have the illusion to live in the same reality, and that's comfortable, and you have no possibility to undermine that. That's the reason why we are so we are believing so hard to that, and that works very well. But if you switch to the meta level, that's not true. But you have no consequences. Okay. Okay. That also, but you know that all these perspectival interpretations allows to solve the Ipria paradox, and there is no non-locality, because as every measurement is relative to one observer, to get the Bell's violations, the correlations that shows that Bell's inequalities are violated, are only built when one people meets the other at time-like interval. So there is no non-locality in this case, but that's the case for all that perspectival interpretation. Okay, so I finish by that. Which extended Wigner's friends assumptions are we following? Universality of quantum mechanics, yes. Absoluteness of observed event, no. So I escape the no-go theorems. Locality for observed event, yes. No superdeterminism, yes. Tracking assumption, no, and that's a crucial point. And a super observer can undo a measurement. I don't need that. I'm open. I have no real opinion about that. Of course, if you accept universality, you should accept the possibility to undo a measurement. But I don't need that. This is not an assumption that I need to build my interpretation. Okay, thank you.
Thank you. So there was a time when you were considered crazy. Now, in the meantime, everybody got crazy. So.
Thank you for the great talk. I agree with a lot of what you say, but I wonder about the following. So, in what situations am I entitled to actually believe what I see? Say, I see you experience something, right? Like you nod now, and you think like you're probably thinking something, and you're seeing this crowd in front of you, right? But maybe your mind just selected a completely different part of the superposition of the wave function, and that could just be an illusion now for me, or could it? So under what conditions can I now trust what I think you see, that you really see it?
I think that there are two ways to answer your question. The first one would be to stick to usual classical realist position. Meaning that when you say, how can I trust that, how can I be sure that you have in mind what is usual for anybody. There is one reality, and then I'm inside, and I want to be sure that what I see is correspond to the reality. I think that it's, of course, natural to do that, and everybody acts like that in the usual life. But this interpretation contends that it's wrong. And is it a problem? No. Because you can act exactly as if it were the case. You will never have any event happening showing you that you are wrong. So you can live exactly like before. Nothing is going to change for you. You only know in your mind that this is an illusion. But this illusion is very well built. It's strong, and you are able to live exactly in the same way as it was true. So there is no problem.
So when I think of my little daughter in the morning, she's smiling at me, and it means what convivial solipsism predicts, and that agrees with my experience, is that I can have a very pleasant morning. I can live my life without having to hear screaming around me, right? But is there really somebody feeling, say, I'm happy and loving me, right? So as you can see, like I want to ask more than just going, oh yeah, if that's an illusion, is that an illusion according to convivial solipsism, at least sometimes?
I received one time a letter from somebody saying, how can you live thinking that? Because you don't know if your friends are your friends. If yeah, that's true. And my answer is that as soon as there is absolutely no possibility to see a change, you can act exactly as it was true. And assume that from your birth, at the beginning, when you're a baby, you are used to live and to act and to think and to as if everything was true, and that works. Okay.
You can apply this for today's talk as well in convivial solipsism.
Yeah.
You can behave as if it is true what is.
Yeah, well, let me take an example which is not very, very good. It's limited, but okay. You know that we are on Earth, and Earth is at a very high speed in the solar system and things like that. Okay, and if I tell you you are at I don't know 20 kilometers per second, I don't remember exactly what is the speed of the Earth around the sun. Okay. In this moment, you are running at 20 kilometers per second, and you tell me, okay, no, I'm great, I'm on my chair. And that's true that you are at 20 kilometers. But for knowing that, you have to be outside, and you have no effect of that. But that's the case. But you can forget about it. Act as if you were on your chair, totally quiet. That's a limited analogy because you can explain many things that are contradicting this analogy. But that's a kind of analogy. If there are many things, I think, in our life that we don't know at all, and that if we knew that, we'll change our way of thinking about the universe or the world, because just in our mind that will change things. But in reality, in the way we live and we act and we are here, it would not change anything. And I think that we are ignorant of many things of that kind. And the example of the speed of the Earth is one example. It's not a good example, but I think that we can find many.
Any other question?
So thank you for the presentation. The whole story about the different ways of looking at the experiments, the no-go theorems, I think is very, very clear. I have a question about, so I want to press this point of like, there's no difference, right? Like I can act as if we are all in the room, even though certainly some of us are on a different branch and they're not here, right? But I see them here and so on. Like, as you said at some point during the talk, there is no way to verify the assumption, the tracking assumption, right? There's no way to verify that what I'm seeing is exactly what you are seeing, right? I can only verify that if I ask you what you're seeing, you're gonna agree with me that we are seeing the same thing, right? Yeah. So somehow, what I see in the world, like the empirical facts or the phenomenological facts, I think you call them, we are in this room and we see the same things and so on. And then somehow somehow we are compelled to complete the world beyond what I actually can verify empirically and directly, saying, okay, there are things actually, there's not just what I see that you see, but actually what you really see beyond what I could possibly ever verify, right? So I'm compelled to, like you're compelling us to add this element to reality, and then you're telling us, well, I'm adding this, and this thing that I can never check is completely different from everything I can actually see, right? Like somehow it's like the real location of you is different from the location of you, and this real location of you has no empirical effect on anything that I could ever observe, right? And somehow, I don't know, it's a bit strange to add something to the description of reality for that thing to actually have no relation, no relation to what I actually observe, and no bearing on reality itself, right? On the reality that I experience. So you see where I'm going there. Somehow I think I'm kind of moving in the direction of Eric Cavalcanti of saying, like, if we can't even verify the tracking assumption, why do we even formulate it? And why do we want to, why create a reality in which I can formulate the tracking assumption only to deny it immediately?
That's an interesting question, and that's a question that's the discussion I had with Eric Cavalcanti. Yeah, I think that what we do when we do physics is building theories with the goal to describe some empirical facts. Okay. Usually with classical physics, we do that very, very easily because that doesn't brings any metaphysical problems. Well, modulo some, okay, let's say that. With quantum mechanics, things become different because it seems that we are at a level where the theory that we built brings some paradoxes, and we have to get out of those paradoxes. And once more, I use the analogy with mathematics. When, as a mathematician, you build an axiomatic formal system, you are able to prove a certain number of formulas of things, and that become theorems. But you want also to be able, as a mathematician, to describe the properties of the system. I use a very simple example. If you build a formal axiomatic system, and then you have a formula, and then you want to express the fact that this formula is true. As you know from Gödel's theorems, in any axiomatic systems, you have true formula, but you cannot prove them, okay? The fact to say that it is possible to have true formula that you cannot prove is not something that you can express inside the system. So if you adopt the attitude that you mentioned, but I transpose that to mathematics, that would mean that, okay, you have a formal system, you can prove things or not, but that's it. And I don't want you to mention things that you cannot prove or disprove inside the systems. And that would be very limited, because what we want to do is to have a system that can do many things, but we, as a mathematician, we want to be able to analyze what I have created and knowing the limits of what I created. And it's the same kind of way of thinking. We build quantum physics, and quantum physics tells you a number of things very interesting. But at some times we reach a paradox, and we have to get out of that. And that's not a proof. I'm not Gödel. I cannot prove what I mean. But an intuition is that we are at a point where we need to go outside of quantum physics, saying things that are not included inside what an observer inside quantum physics could say, to express a property of the theory that we have created. And in a way, this striking assumption that is not possible to observe inside the quantum physics, because no process, the quantum process, is able to put that in evidence empirically. But as a creator or builder of a theory, it's interesting for us to be able to speak, to mention that, and we have to get out of the theory. And so I want to be authorized to speak from the outside of the quantum theory, which is describing all what I can experiment, but not everything I can think. I want to be able to think of things that quantum physics is not able to describe. And that's things that many physicists don't like at all, because they want to stay inside quantum physics. And when you mention things that are not experimentally testable, they say, okay, that's metaphysics, that's philosophy, that's not interesting. And I think that we are not only physicists, we are also thinkers. And as thinkers, we have the right to think about what we have created. And sometimes you need to get outside of what you have created just to mention the limits of what you have created. My first book, the book I wrote in 2000 in French, was the title was The Limit of Knowledge. And that was a book where I examined all the fields in different disciplines, physics, but also mathematics, also epistemology, all the reason why the science itself has set up limits for its own discourse. The most famous is the Gödel theorems, of course, but there are many others. And for example, in physics, in physics, we know, and we can prove it, that it's not possible to predict the behavior of a chaotic systems beyond a certain horizon and things like that. So I analyzed that in the book, in many different disciplines. Of course, mathematics are the best way for doing that. It's easier. But science can sometimes prove that limits are there, and that science is not able to go beyond its own limits. That's a little bit the idea. Okay?
Right, I see. Yeah, thank you.
Thanks for the talk, first of all. I'm now a bit confused as well about the interpretation based on what you said about the tracking assumption and the rest of AOE. Okay, when I think about probabilities in your interpretation, and for example, I have a joint probability, what does this mean. So I have my observed like EPR or whatever, or this joint thing in the LF setups. So I have now a joint probability of me observing this and my counterpart, the other Wigner, observing the other thing. If I understood you correctly, this means that I have my observed result, and then whenever I talk to that person, I will get presumably some relative frequency that matches this probability, right? Not saying that this is what this guy actually saw, right? But if I now think about the tracking assumption, I can also think of this as me then asking the guy in the box, what did you see? And then I get, well, then I'm inferring, it seems to me that I'm inferring the same kind of thing. So I perform my X0 or whatever measurement, ask my friend inside the box, and then this outside information I get, I'm assuming by tracking assumption that this is what this, well, I mean, not that this is what they saw, but that this mathematically is a delta. Can I not read this delta that I do some identification between the two, but just like I do for the joint probability when I actually ask my counter Wigner what they saw. So I don't see, but you only want to get rid of the tracking assumption. So for me, it looks as if in your interpretation, in some sense, they are the same kind of, they represent a very similar thing. So why would you want to uphold one and not the other? You know what I mean? So I don't see the so you say you get rid of the tracking assumption.
Yeah.
Right? Okay, now, so this mathematically for the LF theorem means, okay, no, I just reject this one assumption that I make that this conditional probability is a delta. Okay, good, meaning I get out of the no-go theorem. But if I now try to think inside your the interpretation you propose, and maybe I'm doing this wrong, this to me is very much the same as saying, okay, this joint probability is given by these numbers that I can use this probability calculus for the joint probability and do, well, it corresponds to what I just said. Exactly, or in the LF sense. So I don't see why I would say, okay, I reject the tracking assumption, but the rest is still somewhat sensible or better, or I can maintain this, so the joint probability I plug in there is still, corresponds to the relative frequency, regardless now of whether this is reality or what this, you know what I mean? I'm doing the same kind of reasoning.
Yeah.
I say this one thing I should not uphold, but the other one is still fine.
Yeah.
But
Yeah.
you're saying that sometimes we use tracking. And in your Bell experiment, we use the tracking assumption.
Or it looks as if, that's what I mean.
It looks like. It looks like.
No problem. Let's say it looks
Exactly.
Yeah.
we never get into trouble by taking this.
Yes, but here in LF,
Extended Wigner strength,
you say this is what creates the problem. So
I think your answer was, it's not true in any case, but it's certainly useful to understand when it can be used, as if it's true and when not. I change a little bit.
yes,
Yeah.
no, exactly, but because they look the same from how I try to read probabilities in convivial solipsism, and then why is one now? Why can I get away with one but not the other?
I'm not sure to have really understood, but I can say something about perhaps tell me if I'm correct according to your question. When I use joint probability, this is, let's say, P, A, and B, just two people. Usually, when I use that, I mean the result gotten by Alice and the result got by Bob. And they are supposed to exist simultaneously, so I can build a joint probability for that. Okay. In my vision, A and B are not, I'm Alice. Okay. If I mention A and B, that would mean A, the result I got, and B, the result I heard Bob telling me that he got. So I have also the joint probability. But this joint probability is about two events that I, Alice, have experimented. Not, and the fact to assimilate what I have heard from Bob B, that I have the right in my interpretation to mention because that's my experience, to what really Bob got is the tracking assumption, which I deny. And this is the reason why when I come back to Bell, I get the same correlation. Okay, so I violate the Bell inequalities. So that I don't violate quantum mechanics. I respect quantum mechanics and I violate quantum the Bell's inequality. But the way I violate them is different from the usual way. The usual way means that if I compare two results, then the results I got and the result I use for violating the has been there well before. And this is the reason why there is this non-locality, because it is assumed to have existed well before, so that's a space-like interval, and that's not possible. In my interpretation, the second result, which is correct, is gotten at the moment when I ask the people. So there is no violations of causal, well, no space-like interval.
Yes, no, what I was saying is, okay, so this is how you read the joint probability, and this corresponds to the number that you get from quantum mechanics, right? Okay, so now I do what to me very much feels the same with the guy inside the box. So my conditional probability P of, what is this, A given C, given that X is the one where I read out the result, I will never get a contradiction, like, okay, so then I say this is the probability of me hearing what the friend inside the box saw, and I write this as a delta. I will never get an empirical disagreement there for precisely the same reason. But somehow this is and this is how you say that's what probabilities are in your interpretation, but for some reason now you don't want to take the second thing when I talk about the friend inside the box and use it for doing the math that corresponds to the no-go theorem. And my question is why? Because this really seems to me very similar to how I established joint probability, right? So there is my subjective, and then I get this other ingredient that I just get second-hand, right? And by virtue, quantum mechanics gives me the numbers that I plug in there or the correlations that I can establish. But, and I do see there is a bit of a difference, but I cannot point it down. So why is this? Okay, so I asked that guy, and that's how I read the probability. But you tell me I cannot put this delta there, and my question is why?
You cannot put the delta, which is the tracking assumption.
Exactly. Yes, the tracking assumption is taking this and putting a delta there, and I'm not like, why is this bad?
I think HERVE is insisting that there is no tracking assumption in no circumstances.
Yeah. Yeah. Yeah.
Then HERVE, you are then all us explain why it works sometimes as if there is true and sometimes not. I think you are asking this.
Yes, this is exactly so.
This is very deep question. We cannot maybe answer now. Sometimes it works. Sometimes it works as if.
I mean, it works in exactly the sense that one of the ingredients is not my first, is not the.
Why do you think that it works? Why do you say that sometimes it works?
Is at that moment when I meet, you said, right? Before, but I can assume that this person got this result before we meet. There's nothing wrong. We can even test this sometimes. Like we can measure sometimes in different settings, and sometimes will be the same setting. I will get plus, and I will say, oh, he has this now minus. I write even before I meet this person. This person has
And this is okay. And this is the point. You cannot say that, even if you have the same. No, it's not true, because no, it's not true. Of course, it looks like, but it's not true. And the reason why is that you reason saying that I got plus, and it appears that in a z direction, for example. And when I meet my colleague, it happens that it also measured in the z direction, and it found what here is the opposite. Okay. Now that will be perfectly okay. But from that, you're not allowed to say that really your friend found minus 10 minutes ago. That's not true. Because your friend, before I asked him, was in a superposed state, and for me, in my reality, nothing happened. And assuming that the reasoning that is usual in the pair case or for violating Bell's inequality, but in the case of the same direction, the usual reasoning is a counterfactual reasoning. If it has been different before, it would be different now. So I assume that it has already been like that well before I had that's a little bit okay. And I refuse this reasoning.
But I think Veronica's question was brilliant. But nevertheless, we will not get into contradiction if we would assume that a result has been established at the moment when I got plus. There's no contradiction. You can keep your view. I'm not challenging this.
Yeah.
I'm saying I can keep also realistic view, and we will agree on this one. But then we come to the extended Wiggins-Frank, and we cannot keep this. Realistic view will fail.
Mm.
So my assumption that there was when I open the box, that the friend sees what was there still before opening the box is wrong. This is with other assumption. So sometimes I can assume, or Marcus with his daughter can assume that she is really happy when he experiences happy, but in extended Wiggins-Frank, it doesn't.
Yeah.
Now I think the question is, how should we, in quantum theory?
Okay. I understand. Okay, thank you. Okay. Well, the answer is, as in many similar cases, when you have something that is not working in many situations, but very precise situation, it's not working. But for more fuzzy situations, it could work. What you have to do is to think that in general it doesn't work, and it's not because it could work in this case that it worked. That's my answer. The reason that I think it doesn't work is that in many other cases it doesn't work. So in this case, nothing tells me that it doesn't work. But as I know from outside, from elsewhere, that it doesn't work, I have no reason to think that even in this case it works. It's a little bit. Let me take an example. I know, for example, that in many countries, very north, it's cold. Okay, but there is a point on the Earth where I've never been. So it could be the case that it's hot, but I don't think that it's hot. I think that in all that situation it's cold, so it's cold also. That's a sort of uniform principle. And that's a little bit fuzzy as a comparison, but that's the idea. I have no reason to think that it's different in this case, even if I have no proof that it's different.
But then there is the question that it seems to work in many cases. Why? Why is it not total chaos? It never works. What is it that makes it seem to work in many cases?
The reason is the convivial aspect of the interpretation, is that you cannot witness that it is different. It seems like it was the same. So you cannot witness the difference. That's why it's convivial. The fact that it's not the same is not something that is testable, that you can witness. It's something coming from the way the theory is working at the meta level. So the meta level tells you something that you cannot see. And that's the reason why many people don't like that, because they say, okay, that's not something that is empirical, so that's not scientific. Okay, that's more interpretation or philosophical. But if you analyze what those theorems say, then you can infer that it's not the same, but you cannot see that. And in convivial solipsism, I tell you that even if I hear you saying that you saw that, that doesn't mean that you really saw that. But this is something that I can say from the outside of the theory, but this is not something that I can experiment inside the theory, which is describing my experience.
The convivial aspect is then an axiom,
No, not at all. Not at all. I can prove it. That's very easy to prove from with the question of quantum mechanics, because the way I describe that is that I describe you and the system and everything else as an entangled in an entangled way. Okay. Now assume that you are entangled with a system that I have measured. Then in quantum mechanics, it's easy. If I measure the system, then I select one component, and I select the component of you in the entangled wave function that is corresponding to the result I have seen. So that is very easy to prove that I cannot hear you saying something else.
But you don't interpret this as I really seeing that, but as me telling you that I...
Absolutely. Okay. Absolutely. Yeah. You superposed are not an entity having definite thing. You are seeing what you select, but me, as I describe you in an entangled way, I am only able to have probabilities to hearing you saying something.
But then from normal quantum mechanics, let's say, there's always some observable that you can measure that makes you say, oh, he's going to tell me that he saw that, and this is consistent with what I...
Absolutely. Yeah, absolutely. Yeah.
Good. I think we can stop.
Thank you. Thank you. Yeah, it was a pleasure to speak in front of people understanding what I mean.